Okay, I can't count on you sticking around to see this whole video, so here's the gist. I'll demonstrate how to use spreadsheets to quickly enter part data, which is stored into CSV files that are processed by the KiPart utility to create KiCad symbol libraries. It's much faster, less error prone, and delivers more consistent libraries than using the KiCad symbol editor, which sucks donkeys. At the end of this video, you can see how to get this free open source program. Okay, on with the show. If you're doing an electronic design, obviously you're going to need parts. And each part in your design needs a footprint for the PCB and a symbol for the schematic. The footprint is easy. It's just copper and geometry, and it's usually already done for you. After all, how many 44-pin TQFP footprints could there be? But there are thousands of different chips that use a 44-pin TQFP package, and each one has its own arrangement of I/O pins, so each one needs its individual schematic symbol. And with KiCad, unless the part is popular with the hobbyist community, you'll probably have to design the symbol yourself. Unfortunately, designing schematic symbols in KiCad sucks donkeys. Let's see why. As a test case, I'm going to design the 16T245 bidirectional transceiver chip, which is this 48-pin chip here. And I'm going to design that with KiCad and see how long that takes. Let me pull a timer over here. Start KiCad and start the symbol editor. Make a new component, 16T245. First pin. Pin name 1 dir, and it's pin number 1. Orientation to the right. It's an input. That's all correct according to the datasheet. So we put that there. 1 pin down, 47 more to go. Now draw the boundary around the chip. And we're done. Now here are the main disadvantages I see with the KiCad symbol editor. Number one is all the manual operations and the dialogues that are popping in and out slow down the entry of pin data. Plus, some of the pin information gets hidden, so errors are hard to find. For instance, it can be hard to find if you have assigned the wrong type to a pin. You have to open the pin up and take a look. And finally, it's hard to stay consistent across symbols to make all the symbols in your library kind of look the same, and that can be really important if you're anal retentive. Now I want to talk about KiPart, which is a better way to define KiCad schematic symbols. First of all, pin data will be entered using a spreadsheet, which is fast because that's why spreadsheets exist. The pin data will also be visible, so it'll be easier to spot errors. The spreadsheet will store the pin data in a CSV file, comma-separated values. This CSV file will be the input to the KiPart command line program. KiPart will translate the CSV file into a KiCad schematic library. Because KiPart is a program, it's fast. It also does the same thing every time, so the schematic symbols in and across the libraries it creates will all be consistent with each other. Okay, now let's build the schematic symbol using KiPart. Start off by creating a spreadsheet. Name it 16T245. Then I'll go into my data sheet. I'm going to copy and paste my pin names and numbers from that directly. And I've got my pin numbers, and here are my pin names, and I'm just going to cut these out and paste them side by side. And we see we've already got a problem. We've got more pin names than we do numbers. The problem is caused by the voltage supplies, which have subscripts, and they've been divided onto two lines, so I have to correct that. Then I have to get rid of these blanks. Okay, now I'm going to label this column pin and this column name. Put a name for the symbol that I want, 16T245. And I need another field here another column called type, in which I list the pin types, and I'm going to start off making every pin bidirectional, because most of the pins in this case are bidirectional. Then I'll go and correct for the ones that are bidirectional. This is an input. This is a power pin. Input, input. Okay, that's all I need to do for that. And I need one more column, which I'm going to call side, and that's the side that the pins are on, and pins 1 through 24 are going to be on the left hand side. And pins 48 through 25 are going to be in the right hand side. Okay, and that's all I need. Now I can go ahead and save this as a CSV. Okay, I've got that saved. Now I'm going to open a command prompt where I saved that file, and I'm going to convert it into a symbol library using the KiPart command line tool. KiPart 16T 245 CSV. I'm going to sort the pin names and numbers by the number of the pin, so they're going to come out the right way around the boundary of the symbol. I'm going to do fuzzy matching on the fields in the CSV file so that things like bidirectional and PWR will map to the correct pin types in KiCad. And my output is going to be 16T245.lib, and I'll override it if that library is actually in that directory. And there you go. Now we're done. So we have a symbol library for the 16T245. Okay, I've opened up the library that I created with KiPart just to look at what the part symbol looked like. And as you can see, you can draw a one-to-one correspondence between the pins and names that I have and the generated part symbol, compare it to the symbol in the PDF datasheet, and they look the same. Now this is all well and good for a small pin count chip like the 16T45. It only has 48 pins, but when you get up into larger chips that have 100 pins, 256 pins, even 2000 pins, you don't want to create just a single schematic symbol for it. You want to have different units within the symbol itself that correspond to different functions that may be in that chip. For example, with an FPGA, there are banks of inputs and outputs that are all connected to a dedicated power supply for each bank, and so you would want to have your FPGA divided up into symbol for, or a unit inside the symbol for each bank. And we can do that with KiPart as well. We can add a new column called unit, and everything that has a 1 in front of it will be in unit number 1. And everything with a 2 in the front of its name will be in unit number 2. And everything that doesn't have a unit number is going to be grouped together into a common symbol, and that's where all the power supply pins will go, the grounds and the power inputs. And now we can save that again as a CSV file. Now let's create the schematic symbol for the updated CSV file. And I'm going to add one extra input operation here. I'm going to bundle common pins together, and I'll show you what that means once we look at the symbol. Okay, so now we've regenerated the symbol, and we can look at it using the symbol editor. And this is the symbol, the new symbol that's divided up into units. This is unit A. It contains one 8-bit bidirectional transceiver, that's contained within the 16T245. If you look at Unit C, that's the second 8-bit transceiver. And now if you look at Unit B, that's the common unit that contains the power and ground connections, and the bundling has taken common pins and bundled them together into one connection. So there's one VCCB connection even though there are two on the chip, and there's one VCCA pin even though there are two connections on the chip, and the ground pins have been also collapsed together so that you can make a single net connection to this pin and connect to both of the VCCB pins on the chip. And that could be very handy when you have something like an FPGA, which can sometimes have hundreds of ground pins, and you can collapse all those into a single ground pin on the schematic symbol and make your connection there, and avoid a lot of manual labor connecting all the different ground pins. So designing the 16T245 schematic symbol with the KiCad symbol editor took around 12 minutes, and with KiPart and a spreadsheet took around 4 minutes, so about 1/3 as long. And the big reason for the time differences with KiPart and a spreadsheet, you're not spending all your time clickety through dialogues like the pin dialog and the symbol editor of KiCad. But the other big speed advantage is that I could cut and paste the pin numbers and names right out of the data sheet, and that's not always going to be available to you. For instance, here's a microchip data sheet, and I can select the pins and the names, but when I try to right click and copy those, it won't let me because the data sheet is copy protected in some way. Now I'm sure there's a good business reason for why Microchip does that with their data sheet, but it's not immediately clear to me what that might be. So you just have to go in and type all the information in by hand, and I'd still rather type it into a spreadsheet and have it all immediately visible and available to me, along with whatever advantages I get from spreadsheet functions to get information rapidly replicated through there. And I'd still rather do that than go through the KiCad symbol editor's dialog menu for each pin. Now, the place you really win big when using KiPart is for those semiconductor manufacturers that provide all of their chip I/O information in CSV files or in some text file format, like Xilinx. All of the Xilinx 7 Series FPGA design info for the I/O is included in these package files that they put on their website, and I've downloaded the zip files for the Vertex 7, Arctic 7, Kintex 7, and for the Zinc FPGAs, and I've stored them locally, and I can process all those into a single Xilinx library for the Series 7 parts. And I can do that with this command, KiPart, and I have a special reader for the Xilinx 7 format that they use for their CSV files. And I am going to sort the pins by the name, and you'll see why when I show the symbol. I'm bundling so that all the common ground pins and common power pins are all grouped together into single pins, and I'm going to put it all into a Xilinx 7 library, and I'm using the zip files for the Kintex 7, the Arctic 7, the Vertex 7, and the Zinc. And so with that command, goes through and processes all of those zip files and takes all the CSV out, and there you have it. I've now got a Xilinx 7 library with all 93 devices, some of them with up to 2,000 pins, stored in that Xilinx 7 library, so we can take a look at that. Okay, I've loaded the Xilinx Series 7 library into the KiCad symbol editor. As you can see, there are a lot of devices in the library, 93 to be exact. Let's pick one of the smaller devices like this Arctic 7 and a 324 pin package and take a look at that in more detail. The first unit is just an I/O bank, and you can see how the pins have been arranged. It's kind of alphabetical according to their names and their I/O numbers, so you can see that they are arranged in numerical order, but there's also an alphabetical component to this. That's why the N and the P pins are arranged close to each other for the differential pairs. This makes it very easy to lay out your differential pairs in your schematic. You don't have to go searching around for different pin numbers in various places. They're all right next to each other. This was done automatically using KiPart's sorting by name option that I pointed out earlier. Also notice at the bottom here we have, if I can get to it, a single power supply pin. This actually is a bundled pin that represents 5 or 6 physical pins on the actual device. So all I need to do is make one connection on the schematic to apply power to all the pins for this I/O bank. And that's always handy and saves some time. Now let's take a look at some of the other units. That's another I/O unit. This is another I/O unit. And this is where the main power goes into the chip for the main ground pin, auxiliary power, block RAM power, and internal core voltage power. And because of the bundling, this one ground pin here actually represents over 45 physical pins on the FPGA chip, and each of these other power input pins represents anywhere from 4 to 15 physical pins. So by making 4 connections on your schematic to these pins, you've probably connected close to 80 or 90 of the pins of the FPGA, which again, a big time saver there. And the rest of the units are I/O, and then there's all the configuration pins for the FPGA, the JTAG pins, the mode select pins, and the analog to digital converter reference voltages and things like that. And it's convenient to have all this in one place as well. Thanks for hanging in to the end of this video. To recap what I've told you, the KiCad schematic editor is slow, error-prone, and doesn't guarantee consistent symbol libraries. The combination of KiPart and a spreadsheet is fast, error-resistant, and guarantees consistent symbol libraries. If you like what you've seen, here's how to get KiPart. You can get it off GitHub, modify the source code to your heart's content. It's just a Python program, so it's easy to install using pip, and you can read all the documentation over at readthedocs.org. Also check out KiCost, because calculating the cost of your project sucks donkeys even more than making schematic symbols. You'll find it in the same places where you find KiPart. Thanks for watching.